Okay, so welcome to section 2.5. This is a very graphing focused section, and what we're going to be doing is looking at different graphs and how different algebra changes to the function formulas affect those graphs. They can essentially shift them sort of left, right, up and down. They can stretch them, they can sort of compress them, and they can flip them. You can sort of reflect them over the axes, kind of like we were talking about a little bit with our sort of even and odd functions, those kinds of behaviors. So what I want to do first is I'm just going to list all of our possible function translations. So I'm just going to make us sort of a master list, and we're just going to sort of, rather than do one or two at a time, we're just going to sort of make a master list of all of them, and then we'll obviously look through some examples that do each of these different moves. So we're working with, starting with a generic function f of x. So we're starting with a generic f of x. That's our standard sort of go-to function. And what we're going to do is all the different possibilities to shift this left, right, up, down, and many more. So first and foremost, let's do f of x plus or minus some constant value c. What I should say before we start here is c is a positive constant. So we'll use capital C here as a stand-in for a generic number, right? Some generic positive constant. So in this case, we could do f of x plus or minus some constant value on the end. So this is the difference between having, right, x squared versus x squared plus 3, right? So x squared is like our original, x squared with just a plus 3 on the very end, right? We're sort of adding this 3 onto our function. So what we're going to get in this case is two cases. So if we do plus c, what that's going to do is it's going to shift the graph up by c units, right? Or if we think of this in terms of the x, y coordinates, so this is going to be y values plus c. Right, so we can either think of this as in sort of a very generic sense, as just shifting all of our points up, all of our coordinates up, shifting the whole graph up, or we could almost do it sort of point by point and just take all of the different y values. If we have a table, for example, we're just going to add whatever number to all the y's. In this case, right, you could do plus 3 to all your different y coordinates. You would probably expect then if I did minus c, what's going to happen is that's going to shift my graph down by c units. So this is pretty intuitive, right? If I add c, if I add some number, right, 3 for example, I'm going to shift all my values up by 3. If I subtract it, well, then I'm going to shift them down. So this is again changing my y values will be minus c. So that's if I add or subtract on the very end of my function. So sort of after all of the formula is laid out, I just tack on some sort of plus or minus number on the very end of it. The other place we can add or subtract is if we do f of, so x plus or minus c. So meaning in the input, if we actually change the input value within the parentheses, so this is going to be the difference between x squared versus, right, x plus 4, like quantity squared, right? So what I'm doing here, maybe I should sort of label these. This would be like our original f of x. And this would be f of, we'll see if we can squeeze this in, x plus 4. Boy, that's tight. I'm just going to scribble that out and sort of rewrite it so you guys can see a little better. Just the most professional possible looking math. Right? So if I add within the parentheses, right, I'm getting this x plus 4 inside my parentheses, and I square the whole thing. So I'm changing the input values here. If I have, so x plus c, what's going to happen is I'm actually going to shift to the left by c units. This is maybe a little bit like counterintuitive. I think to a certain extent everybody's instinct here would be that if you're going to add, if you're going to do plus, you should actually, right, move in a positive direction, which if we're thinking x's, we're probably thinking to the right. Conceptually what's happening is essentially if we're adding to our x, it makes the input values bigger, which conceptually means we're actually getting to those values sooner. And so the graph, if I used to hit it at like x is 0 and 1 and 2, now I'm hitting it however many units beforehand because I'm adding to those values. So this is going to be x values. You're actually going to subtract the c off of it. Obviously, we'll go through examples for all of these in detail. We're just sort of laying out everything here. If I do x minus c, what's going to happen is that is going to shift me to the right, again, just by c units. And so that's going to be my x values plus however much c is. So shifting left and right is a little bit backwards from what people's expectations normally are, right? So if you're doing x value plus c, you actually shift to the left. If you're doing x value minus c, it actually shifts you to the right. What's happening there, right, is you're kind of losing value from your inputs, so you're getting to the coordinates a little bit later than you would otherwise. If you think of your x values, your input values, almost like time values, right? If you, sort of subtract 30 minutes, if you lose 30 minutes from whatever it is that you're doing, you sort of get to everything 30 minutes later, right? Your graph actually ends up sort of shifting. Everything shifts back from 3 p.m. to 3:30 and 4 to 4:30 and so on and so forth. Pause there and we'll do some more in the next video.